Hey everybody, how's it going? It's Boo from Mile High Distilling. Today I want to talk about yields and runtimes and not just giving you numbers and you just accept it. I want to show you the formulas. I want to show you how we get to the numbers, how we calculate our runtimes, how we calculate our yields so that you can do it too with any size still. Let's say you're thinking right now about upgrading to a still. Maybe you have a 5 gallon, you're thinking about a 13, but you're not sure about your yields, how long it's going to take to do a run. We're going to calculate all that for you, and we're also going to show you again how to do it yourself so that you'll never have to question again. There's a few variables with each of these parts. Your yields, we have a few things we got to look at, and our run times, we have to think about a few things. So for yields, remember, we have to think a lot about our ABV of our yeast. If we have a fermentation sitting at 15% ABV as opposed to a fermentation sitting at 5% ABV, our yields are drastically different there. What ABV means is that, let's say we have a 5% ABV solution. That means out of the volume you have in your fermentation bucket, only 5% of that is alcohol that you can collect. So as opposed to 15, obviously you're going to get a lot more out. Now, another thing we have to take into account there is that different spirits and different fermentations are going to produce different amounts of volatiles, which will cut into your cuts. So if we have a sugar solution that we're fermenting on with a relatively low amount of methanol content, we're probably going to get a little more out and have to take less away from our cuts than opposed to something like a fruit, which produces its own methanol, so naturally has more. For runtimes, we have to base this on a few things too. We have to take into account the heat source we're using and what that's producing, because that's going to affect our heat up time. We have to think about our diameter size of our tower, because that's also majorly going to affect the output per hour and how long runs will take in conjunction with the boiler size we're using. And honestly, it's early in the morning for me. I'm probably missing a few things. We'll go through it. We'll talk about it all by the end of this video. Let's start with finding our ABV. What I'm going to do is I'm about to cut to a chart here. I made a little flow chart for you. What this has on it is a bunch of really popular boiler sizes. It's a mix of our own boilers we sell here, because obviously I have those numbers a little better, as well as popular sizes I see people have. From there, we're going to try to calculate with our headspace, because remember, that's another variable. We can't fill that 13-gallon still up all the way. What happens when you put a pot of water on the stove and boil it when it's full? It's going to overflow, right? Same with the still. So we have to account for a little bit of headspace, and depending on the design of the still, this gets more or less, but I'm going to give you a rough figure. I can't speak for every still on the planet, but you're almost always safe with just a few inches off the top. So we'll put that in there, get you a good understanding of what your, I guess, volume will be. Not really your max capacity, but in a way it is. It's really all you can put in the still. And then from there, I'm going to show you how to calculate our ABV so that even if you're not at 15%, whatever you're at, you're going to be having the formula in front of you. You can run it, and it doesn't matter what your ABV is at. So as we can see here to start, in Tier 1 in the dark blue, we're going to see different boiler sizes. This is a mix-up of boiler sizes we sell as well as just popular ones I see around. 1 and 2 gallons are units we don't sell. We think they're too small. But Vivor does, which is a very popular still manufacturer. That's because all the corporate conglomerates sell them, and they're made very cheaply. They are cheap units to buy. Not trying to knock them. If they work, they work, but they're up here. They're very popular because of that reason. 3 gallons is a unit we sell. 5 gallons is, I would say, one of the most popular still sizes. 8 gallons are our most popular still sizes. 13s are very popular units. 16 is something we sell, as well as 15.5 is what kegs are, and those are popular. 26 and 53 are units we sell. They're a little bit of oddball sizes, but it's going to show you too how much your volume changes as you go up in a still. And then I threw 300 gallon in here just for a little bit of fun. We're going to see some crazy numbers on that. So what we'll see here is in this Tier 2 in the light blue, we're going to see sort of what I accounted for on Headspace. The units we sell, I know for sure. Units not found here was just kind of a guess using the best of my knowledge. You'll start with, 1 gallon, take about a quarter gallon off the top, and that should give you some headspace. As you proceed down this list, it's going to take more than a few inches off the top. So we'll start seeing that change from just a measly half gallon, quarter gallon to, sometimes you have to take 1.5 gallons, like with the 8-gallon unit, off the top just to kind of get to that capacity. And then we shoot all the way to 300 gallons, where you're going to have to take a full 5 gallons off the top to sort of leave room for that headspace. Obviously it goes without saying, but if you guys need to pause the video and actually like look a little harder on what's going on, feel free to do so. I'm just kind of speeding through it, just getting the gist of everything, just because I don't want this video to be 30 minutes long. We still have a lot to talk about. We proceed through tier 3, which is the green star, and we're going to be looking at our total volumes. This is without cuts, without anything diluted. These are what the volumes we can expect out of the units we have. This is based off a 15% alcohol by volume solution. So you'll see there, that first number I give you is, let's look at 1 gallon. I have 0.75 times 0.15. I have 0.75 in there because remember, our capacity after we leave room for headspace is 3/4 of a gallon. That is 0.75. And then we're going to multiply that by 0.15, which is 15%. And that's how we get our figure. So if you have 3%, it'd be 0.75 times 0.03, and you get the gist. That's going to give us a yield of roughly 1 pint. It's 0.1125. For the conversion with the pint, all I did was I put a gallon converter in and 0.1125 in the gallon side of things, and then that translated to pints. You can do that pints, fluid ounces, cups, whatever you really feel like doing. As we proceed down that list, we're going to take a look and we're going to start seeing some big jumps here. In fact, even the jump from 5 to an 8-gallon still. We're going from 0.6, which is about 5 pints or so, to 0.975, almost 1 gallon. So we're getting like 3 extra pints from that jump from a 5-gallon to an 8-gallon still. And it only goes up from there. We're going to start seeing into the gallons. We're going to start seeing, upwards of 7.5 gallons with a 50-gallon still. And then with that 300-gallon, we're talking about almost 45 gallons worth of spirit in 8 hours. Things get pretty insane with stills. So take that into account when you're purchasing. Run this figure based on your estimated ABV, whatever yeast you really like, whatever is your favorite yeast, run that number. And then just for a little bit of fun again, I wanted to go ahead and throw in tier 4 in the pink and purple the amount of 12-ounce mason jars you should expect when your run is finished. This is what I use primarily, 12-ounce mason jars when I distill. You're free to use whatever you want, 32 ounces, gallon jugs if you want. But I wanted to show you, let's say you're running a 5-gallon still and you're using 12-ounce mason jars. Well, you should expect 6.5 gallons full when your run is complete. If you don't get that, there might be a trouble with your yield. You might not have gotten the ABV you want. It'll give you a good guideline to look for if you're not achieving what these numbers are saying. And then I also want to mention how crazy things get. Can you imagine trying to collect 300 gallons of liquor in 12-ounce mason jars? You'd end up with 472 jars sitting in front of you. Literally such a big number, it turned my circle into an egg in this chart. So now we have our total yield calculated. Now it's time to play with some of our cuts and try to figure things out there. Because remember, not all of that yield is going to be good stuff. There's going to be methanol in there, acetone, acetaldehyde, different things, and then later on in the bad part of the tails, we're just going to get some nasty, bitter things that we don't really want to carry over or drink. This one's hard. I'd really like to be a scientist or talk to one and sort of figure things out more precisely than what I can. What I figure, and I'm by no means an expert distiller, so maybe someone in the comments can give me a better figure that they use. I figure about 25% of my total yield is going to go to my cuts. Now that's based off, again, I generally don't work with fruit. I work with grains, molasses, agave, sugar, and all of those are going to have pretty low methanol content. So that's where I get my figure. If you're working with fruit, I think sort of a better figure would probably be about 33%. I've worked with fruit a handful of times. It's been a long time though, so I could have my numbers a little bit off. I reckon about 33%. And let's factor that in to our yield. So let's just do this all. I'm going to do this with you guys. We can just get a nice formula down. So for the sake of this video, let's pretend I have a 16-gallon still, which with my headspace is going to be about 14 gallons full. Let's say I'm at 14% alcohol by volume. And what that's going to equal is just shy of 2 gallons. But for the sake of this video, I'm going to pretend it's right at 2. 2 divided by 4 is 0.5. And that means if I have 25% of my cuts leaving the total volume, we're just going to subtract 0.5 from our total volume. That's going to equal 1.5. So my yield of collectible drinkable spirit should be 1.5 gallons. Now here's where things start to get tricky. Remember that spirit is coming out at a higher proof than I want it. So how are we going to calculate our yield? Obviously when we dial things back we're going to get more out, but just how much? So how we calculate water dilution and what it's going to do to our spirit is a little something like this. We turn our proof into ABVs. Remember your ABV, alcohol by volume scale, is always half of what your proof is. So if we're at 160 proof, we're at 80% ABV. So our first number is going to be 80. From there, we divide by the alcohol target number we're going for. If we're trying to bring this down to 80 proof, that'd be 40%. So we're doing 80 divided by 40. And then what we're going to do is multiply that by the total volume we have. In this instance, it's going to be 1.5. We're going to go ahead, that's what the calculation looks like. I'm going to go ahead and tally that up. What that number is going to be is 3, just a full-on even 3. And now we're going to subtract our volume from that number. 3 minus 1.5 is 1.5. So this is our formula we're going to be using to dilute. Obviously I picked real easy numbers so it's nice and easy to understand. Of course we're going to end up with half. So if we're trying to bring 80% down to 40%, we have half water, half alcohol in our jar at a time. And that's how we get our formula. So 1.5 gallons would take 1.5 gallons of water to get to our target 40% from 80%. So now to really have it sink in, let's do this with a little bit harder of a figure. Let's say we're at 135 proof and we're trying to bring it down to 85 proof. So first, with ABV, we simply take our proof numbers, divide it by 2. Half of 135 is going to be 67.5. We're going to divide that by our 85 proof. Half of that would be 42.5. We multiply by 1.5, which is our yield, what we have right now, our volume. What that number will be is 2.38. Now, to find out how much water we need to add to this solution, we just have to subtract our total yield, our 1.5, from 2.38. And that's going to equal 0.88. So we're using just shy of a gallon of water to bring 135 proof down to 85 proof. Now, how does this correlate with our total yield after we make our cuts and after we dilute? How do we find out how much? Simple. You're just going to take that part of the equation out. And here, right here is going to be your total yield after everything's said and done. You'll have 2 gallons, 2 and a little under 2.5 gallons of 85 proof spirit when you're all said and done. Now before we proceed into the second part of this video where we talk more about run times and everything, I want to take a second here and like I always do, I wanted to thank you guys for watching. I really enjoy doing these videos, and from the feedback I'm getting, it seems like you guys do too. If you're enjoying the video, please be sure to leave a comment saying how much you're enjoying it. Give me some tips, give me some video ideas. I got a really great one from one of our customers last video. As well as be sure to like and subscribe if you're really enjoying our content. That helps us thrive, grow, and continue to do this for y'all. And also, guys, I think you guys know the drill at this point. Take a shot with me, people, okay? What I have here is a beautiful spiced rum made at Balmer Peak Distillery. It's got an amazing color. Really happy with how it turned out. Very well rounded. We call it the Rum Forest Rum. Absolute perfection. Also, what we did, just so you guys know, is we added a little bit of molasses and a little bit of honey directly into this bottle. That's going to increase the viscosity of it, which will give you a better mouthfeel. It also changed the color significantly. We're really happy with this color. That's because of the molasses. And then it also just sweetened everything up, made everything a bit more well-rounded, some of that harsh cinnamon spice, you know. So all in all, pretty happy with this, happy with how it turned out. And when it comes to run times, as I mentioned earlier on in this video, we have to pay attention to a few things, and namely what those things are going to be is our heat source and how much heat that's pumping in the still. That's going to determine our boiling time to get up to temperature. We also have to think about our diameter of our tower. Now, heat is going to be a doozy for me to explain, especially because, wow, there's a lot of numbers and figures associated with that. I'm going to do my best to present them to you and help you calculate. But let's start with something a little easier. Let's talk about our tower and how that affects our runtime. Essentially, a good rule of thumb is every time you move up in a diameter size by an inch in your tower, you are effectively halving your runtime. So a 2-inch tower can produce around a quart per hour. When you move into a 3-inch tower, we're now at 2 quarts per hour. And then from a 4-inch tower, we're going to see a gallon, another jump double in your output per hour. So as we're doubling our output per hour, we are halving our run time. So take that into account when you're building a still, if you're trying to purchase a still, and seeing what size diameter that tower is. Remember, most towers in this industry are going to be made of tri-clamp fittings, and tri-clamps have an interesting measurement on them. A 2-inch tri-clamp measures 2.5 inch outside diameter. 3-inch tri-clamp measures 3.5. So pay attention to that outside diameter, and that's going to tell you, how fast you're going to run. Another thing to think about a little bit is depending on how you're running, that number is going to change, that output is going to change. If you're running a reflux system which has 2 condensers, you're going to be slightly slower than you would if you were running pot still with only 1 condenser. That takes more time to process. With a reflux system, your vapors come up, they get to this first chamber, push back down, and then reboil as lighter vapors again. So that takes time to go through that process. It's pretty minimal as far as I've seen. It really just depends how slow you're running. If you're running reflux system as slow as you possibly can for the highest proof possible, you might see a pretty decent chunk in time as opposed to running a pot still as fast as you can. And with that said, the output that you choose to go at is also dependent on your runtime. You can, if you have a precision control box heating your still, and some people are good enough at propane to do it that way too, you can switch your flow. You can go from a pencil lead thick stream out of that condenser line, or you can slow down that heat, shut off on your water a little bit, and get down to a drip, drip, drip. And that's obviously going to affect our output. What we need to figure out is our initial temperature point, which is pretty easy. That's the temperature point as your volume, your liquid, enters your still. So take a thermometer in there, stick it in the boiler. It's 80 degrees. We have that number. Now we need to figure out the boiling point of our solution in there. We know that ethanol boils at a true state of 173, but then comes our first issue. Those numbers aren't exact for every single location. Depending on your elevation and depending on the ratio of ethanol to water in your boiler, that number is going to change. It doesn't always be 173. It's there as a guideline, but there's much more to it than that. So for the sake of this, let's say it's 168 degrees. That's the boiling point of our solution in our boiler. Now what we do is we take our boiling point, 168 Fahrenheit, and we subtract 80 from it, which is our initial point. That'll give us a figure of 88, which means we need to push up 88 degrees higher in order for things to start boiling. Now here comes the real headache. To do that, we need an immense amount of info. We need to find out the kilojoules and basically how much energy our heat source is going to use. We need to translate that into how much energy it takes per unit of measurement. So for example, let's say you have a 120,000 BTU burner. That's going to translate into about 126,607 kilojoules of energy. Usually that would translate into grams. So basically you'd use 126,607 kilojoules of energy per gram of fuel. Okay? See where it's starting to get complicated already? From there, we need to figure out the weight of our solution. We need to figure out how much volume is needed to heat 1 gram. We need to correlate the gram from our volume, which is very hard to do. Let's say we were doing water and boiling water in this instance. Well, 1 milliliter of water is going to equal 1 gram. So it's an easy measurement, but alcohol is different. You need to first figure out all that. Once we have all that info, we need to run this equation. Guys, I can barely dress myself. I'm not smart enough to answer this equation for you. However, I can tell you what it all means. We're trying to solve for Q, which is going to be our energy, how much energy we need. In this instance, the M is going to equal our mass, or basically the weight of our solution. C is going to be our specific heat capacity, which means that it's going to be the amount of joules per grams of Fahrenheit, basically. Or Celsius, up to you. And then our delta T is going to be our change in temperature. And then from there, we find our molar mass of our solution. If it was 168, I think it'd be something like 45. And then basically that would be per gram. So 45 molar weight per gram. And from there we can, dial in everything. However, I just took a pretty big break so I could stop the one brain cell I have from exploding. And I edited the video, realized we're about 25 minutes in. And another thing is I kind of have a rule for myself. I don't usually speak on things unless I know what I'm talking about. Kind of my golden rule. And I think I realized that as much as I'd like to help you on this one, I'm going to provide a calculator, a few resources for now to help you determine through running through a calculation. And what we'll do is I'll do more research on my part and maybe introduce in a later video a better solution for this. Now down below in the description, I'm going to include a link to the best calculator I could find for what we're trying to do here. There's a lot out there. Some were pretty confusing. It didn't make much sense even when you run the numbers. Some require much more information than I'm sure a lot of you have, such as these joules and this and that. The one I found is pretty cut and dry. It's asked for a volume, it asks for a starting point and a boiling point for your temperatures, and then it just correlates it with a wattage or a BTU. So as long as you have the BTU of your burner or the wattage of your heat controller, you should be fine. Problem is as we were talking with the variables of our solution in the boiler, that calculator is only going to measure at water. So water is 212 Fahrenheit. Maybe you guys can just sort of find that number by subtracting boiling point of water from the boiling point of your solution. But more or less, this is going to be the best resource I have right now to try to figure things out. Now what I can provide is a little bit of info on our stills and how this correlates with heat up time. When we have a 3-gallon still, and let's say it's 2.5 gallons full, again we have a solution with many different boiling points, we heat up when we have a 110 volt controller in about 30 minutes, almost on the dot. So just to give you a rough idea of what you'd be looking at. When we go over to a 220 volt, that is double the capacity, it's going to take about 10 to 15. I've had it at 10 when I have my 220 volt all the way up, but depending on where you're at in your heat source, you could see some changes in that. An 8-gallon still, something a little bigger, would be something closer to about an hour or so with a 110 volt controller, maybe a little under. Then we're talking about 30 minutes with a 220. I haven't run propane, but some of those cookers just get absolutely insane. If you have a 120,000 BTU burner, I think you're pretty equivalent to a 220 volt, 5500 watt heat source, so those numbers should stay pretty universal. They only go up from there. 26 gallon with the 220 volt single element 5500 watt controller. That's going to heat up in about an hour and a half, and we just proceed from there. So guys, sorry I let you down on this one. I just don't have the knowledge to really undertake this right now, and I bit off more than I can chew, so apologies. We will cover this in a future video, and I'm hoping I've given you enough resources to actually correlate that and at least somewhat guess what your heat up time would be, which will help you understand your runtime. So to finalize things, once we determine sort of our heat up time or a rough estimate of it, now we can start thinking about our diameter size, our boiler size, and what our run would look like when we run our volume. Now you guys remember that 2.38 gallon figure I got, right, from our yields? We have 2.38 gallons to run. Let's say our heat up time is 30 minutes. Let's say we have a 3-inch diameter tower, which produces about 2 quarts per hour. Now, if we're at 2 quarts per hour and there are 4 quarts in a gallon, and we're trying to distill about 2.5 quarts, that tells me that in 2 hours we have a full gallon with a 3-inch tower. So double that for 2, that's going to be 4 hours, and then that half is going to take about another hour, right? So all in all, we'd be looking about a 5.5 hour run, and if our heat up time is 30 minutes, that's going to bring us to 6 hours. We can produce about 2.5 gallons of alcohol out of a 3-inch tower in about 6 hours. That's kind of our figure. Just to kind of drive it home, let's pretend we now have a 4-inch tower, which is double the speed, which means 1 gallon per hour. We have 1 gallon per hour and need to get 2.5 gallons worth of distillate out of our still. Well, that runs in 2.5 times. So we have a 2.5 hour runtime with the 30 minutes here. That's 3 hours, half. All right, guys, I hope you enjoyed the video. I hope, regardless of the little bit of trouble we had with the calculation of energy, it still made pretty good sense, and I helped you calculate what you need to calculate to make a good decision on your boiler size and tower size, and also help maximize your runs. Make sure you're getting what you want out, what you are expecting out. Once more, any comments that you guys would like to put down in the comments, please be sure to do so. I love hearing from y'all. And if you have any better resources to maybe help calculate these things, throw them in the comments. Throw everyone a link. Help the community out. Thank you guys so much for watching. Peace, guys.